In question 3, we have two crates. They have different masses. One of them is a little smaller, and the idea is you're pushing the crate like this. So the idea here is that you're pushing the crate with the smaller crate, the 12 kilogram crate, in like where your hands actually touch, and then the 20 kilogram crate is in front. As someone pointed out in class, that's a little ambiguous, that's a little unclear what in front means. Are pushed across a smooth floor. It says the 20 kilogram crate in front of the 12 kilogram crate. So this is what I meant when I drew the picture. So that's the way it looks. Now the question is asking what's the applied force. The other thing that it tells you is that there's an acceleration of the acceleration is equal to 1.75 meters per second squared, and it's pushing in that direction. So in order to find the applied force for the two crates, we're gonna treat them as a system. So I'm gonna sort of draw this gray circle around both crates. And you can imagine that if I treat the two of them as if they're one unit, then the only applied force, or the only force that's acting on the system, is the force of the push. Technically, it's acting on the 12 kilogram crate, but in this case, I'm effectively treating the 12 and the 20 as if it's just one thing, because it's moving as a unit. So I feel justified in doing that. So looking at this free body diagram of the two masses combined, I set up my F-net statement, which is F-net equals the sum of the forces, which equals to MA. In this case, the sum of the forces is simply the force of the push, and that equals MA. So what we're trying to figure out is what is that force of the push. So that can be found using the combined mass, which is 12 plus 20 kilograms, and then the acceleration, which we found to be, or which we're told to be 1.75. So when we put all that together, we find the force of the push must equal 56 newtons in order for that to make sense. So that is the first part, part A. And we figured it out by treating the two blocks as if they're one block. In part B, we want to know the action-reaction force in between the two forces. And for this, I've drawn the two crates sort of separately. So we're going to actually draw free body diagrams of each one. So for the smaller one, the 12 kilogram crate, there's still the force of the push. That's the one that's actually touching it. But there's also this other force, because what happens is the 12 kilogram block is going to crate is going to push the 20 kilogram crate. That's the actual force that's accelerating the 20 kilogram crate. I'll call it the force of 12 on 20. So then the reaction force to this will be the force of 20 on 12. And those two forces are action-reaction, Newton's third law forces, which mean they're equal in magnitude, opposite in direction. And we know also that each of these crates is accelerating with a rate of 1.75 meters per second squared, because that's what's given to us in the question. All right, so then I can use either diagram to figure out the answer to this. We want to know what that force, the 20 on 12 or the 12 on 20 is. We want to know what that force is. I can use either free body diagram. Just remember that when you use a free body diagram, when you draw a free body diagram, you have to refer to it when you do your statements, your F-net statements. So this question was part A. For part B, I'm going to say F-net equals the sum of the forces, which equals MA. Now for this, my sum, let me say I'm working with this let me call this free body diagram 1, okay? And let's say I'm working with 1. So I'm going to look at that. So what are the forces acting? The sum of the forces? Well, I've got two different directions. So let me clearly articulate which direction is positive and negative. So I've got the force of the push in the positive direction minus the reaction force, or the 20 on 12 negative. See, I've subtracted it. And that's all going to equal MA. So I'm only looking at free body diagram 1, so let's substitute in what we know. We know from part A that this force of the push is 56 newtons. We don't know this. That's what we want to know. We want to know force of 20 on 12. And we know that the mass that I'm looking at right now is 12 kilograms. And we know the acceleration is 1.75 meters per second squared. So I can solve this. 56 newtons minus the force equals, now 12 times 1.75 is 21 newtons. Kilograms times meter per second squared is a newton. So then I can rearrange everything. Force of 20 on 12 equals 35 newtons. So that's my answer to part B. And I could have solved that either way, either using the free body diagram I did use, or like I showed you in class, and I can make it explicitly here, I could have used the other free body diagram, the one that you can see in the top corner of the 20 kilogram mass. So the alternate way to do it, alternate, how do you spell alternate? It's way. And this is using free body diagram, let's call this 2. Okay. So then in that case, we start the same way. F net equals MA equals the sum of the forces, which equals MA. Now the sum of the forces here is just the force of 12 on 20, and that equals M, which is, in this case, it's 20, because that's the free body diagram I'm looking at, times 1.75. And then 20 times 1.75 is equal to 35 newtons. Same answer. Force of 12 on 20 is 35 newtons. So that is the answer. Now you might be thinking to yourself, but I thought they were supposed to be opposite, like one of them supposed to be negative. We actually took that into account right here. We already told the equation that the force is negative, so when we get the answer, this answer here is strictly the magnitude. Both of them, magnitude here, and this is also the magnitude, but we know it's in the positive direction. So either way would have worked. Now in class, we talked about what would have happened if you changed the direction that you made this force. Like for example, if I take this whole diagram, copy it over, and let's just play around with it a little bit and say, okay, now the question is basically the same question, but I want to know what would happen if I switch the direction of the boxes. So let's erase all this fluffy stuff. So get rid of that, get rid of this person, well, you can keep the masses, they're the same. But now imagine that instead of pushing from that direction, we've got the person pushing from this direction. Let's move a little closer. So you've got her pushing, or him pushing from this direction. Okay, so then it's still hard, but now the force is pushing this way and the acceleration is this way, 1.75 meters per second squared. What we said was, when you do part A, the free body diagram is exactly the same, right? Because you treated them as a system. So I put both of them around this bubble, and when I do that, the only force acting on them is the force of the push. So in this case, we can easily say that the force of the push can't change. It's got to be equal to 56 newtons, the same as it was in the other part. But for part B, now it's kind of changed a little, because the free body diagrams 1 and 2 are going to be different. If you think about it, you've got the 12 kilogram crate now. It doesn't have the force of the push anymore, does it? The only way it's accelerating is from the force of 20 on 12. It's still accelerating at 1.75 meters per second squared, but that's all the forces. So now, this was part A. For part B, when I do my F net statement, F net equals the sum of the forces, which equals MA. And so then when I do my this sum of the forces, what's going to happen is I'm going to only have the force of 20 on 12, and that I can make that negative. So you can say negative, because it's to the left, equals the mass, which is 12, times A, which is 1.75. So then this force of 20 on 12 is equal to negative 21 newtons. So it's different. It's smaller. Does that make sense to you? I hope it does. The idea being that when you push on an object, the object has inertia. So this 20 kilogram block has inertia. And when you push on it, it absorbs some of that force to accelerate. If you pushed on just a 20 kilogram block with a force of 56 newtons, you would get an acceleration greater than 1.75. The reason it's only 1.75 is because of this 12 kilogram block in front of it. So it's almost like the 20 kilogram block absorbs some of the force, and the smaller block doesn't need as much force in order to accelerate, so there's less force left over for it to use in this situation.